I wanted to introduce Suzan Verberne from Leiden University, and I copied and pasted this mercilessly from her own website, so you can see the things that she's been working on, a wide variety of topics, from social media to law to archaeology to medical specialists, and she's also part of the 4D picture Horizon project that we're involved in here in Lancaster. She's part of the team, leading the team from Leiden University, where we're looking at metaphors related to cancer discourse in 4 different languages. So Suzanne, as you can see, has worked in NLP, information retrieval, and recently, I think it was a couple of weeks ago, had her inaugural lecture as a professor in Leiden, and I think the recording is online. You can have a look at that as well. So I'll stop waffling, and hopefully Suzanne is there and we can switch over just a sec. So Suzanne, if you want to start sharing yours.
I think this works. Can you see my slides?
Yep, we can. And John's given me the thumbs up that we're recording, so it's all good. I'll hand over to you. I'll just mention your topic. As Goran said, there may be 1 or 2 talks in this conference about large language models. You may have heard of them, but Suzanne will tell us more. Over to you, Suzanne. Thank you.
Yes, thank you, Paul. Hello, everyone. It's not ideal to present online. I'm grateful for the organizers to allow me to give this keynote online because I was not able to travel these days. I can actually see you, but from the back. So my camera standpoint is from the left back of the room. So I can see you. So if things like people nodding, I might see something of that. So yeah, let's get started, and I hope I can engage a little bit in questions afterwards. Let's see how that will work. Okay. So what I'm going to present today is the NLP paradigm shift, and that comes back in my talk a couple of times. So how do we go from supervised learning to instructing large language models? And I will present the results of 2 projects that we did in the past few years. One is about mining the experiential knowledge of patients, and one is about the challenges of biomedical entity linking. And I had a look at the program and the posters that are being presented today and tomorrow, and I see there's quite some posters that are also related to this. The word cloud also showed cancer. Well, this project was also about cancer. And then towards the end of my presentation, I go into the opportunities of large language models and the challenges. And yeah, answering the question, should we care more? Pun intended. Okay, so let's introduce this. I know you're all text analytics people, text mining people. You all have some knowledge of natural language processing, but I always start with a general introduction to the current state of the field to bring everyone on the same page. So the current state of natural language processing actually started in 2017 with the publication of this paper, Attention is All You Need, which introduced the transformer architecture. As you can see, it has been cited a huge amount of times. Right? There are not that many papers that are cited this often. So this original transformer architecture was designed for text-to-text tasks like machine translation. And they are very powerful. One of the reasons for that is that they can identify and compute relationships between all the tokens in a sentence, even if the sentence is very long. So pre-transformer time, like pre-2017, Google Translate would have had difficulties with sentences like these, with a long distance relationship between the subject and the finite verb, right? So the presentation I will give, etc., is about large language models in healthcare. So this now works perfectly fine. And so apart from that architecture, another reason they are so powerful, of course, you know, is that they have millions or even billions of parameters, and they have been trained on huge amounts of data. So they've seen a lot of text. So this original transformer, as I said, is an encoder-decoder model, which means that it takes text as an input and it gives text as an output. So that is perfectly suitable for a task like translation, where we go from text to text, like this. But very soon after that, another type of model was being published and designed that only takes the left side of it, so only the encoder side, where the input is text and the output is a meaningful numeric representation of the words in that text, or the text as a whole, and we call those embeddings. So this kind of models is called BERT, and I'm pretty sure that every one of you has worked with BERT models since 2018, 2019, until now, and still ongoing. They are very powerful because of this pre-training on a lot of data. They have rich representations of words, and then you can fine-tune them for specific tasks, like classification or information extraction. On the other hand, we have the family of models that is only the right side of the two-sided transformer, so only the decoder. That first model that was introduced like that was GPT, Generative Pre-trained Transformer, in 2018. So when I give this introduction to people outside our own field, they are typically surprised that GPT existed way longer than ChatGPT when it became famous in 2022. But the idea of this model is that it can only generate text. You give it a prompt and it continues text. And this is a probabilistic process. So it was trained to generate the most probable word at each point in generating the text. And if you give them sufficient data and sufficient parameters, they are impressively fluent. So later, ChatGPT is a variant of GPT 3.5, later GPT-4, that was trained to have a dialogue with the user. But in its basis, it is a text generation model, a transformer decoder, word by word text generation. But now it becomes interesting because it was found quite soon in 2020 that when generative language models, so decoder models, are larger, when you make them very large, they can do much more than where they were trained on. So the earlier GPT models, so can you raise hands, who worked with GPT-2 before? No one really? Oh yeah, a few people. Yeah, I see the raising hands. Yeah, I can see that. Cool. Yeah, so when we were first working with GPT-2, we had to fine tune it to do the thing that we wanted to do, right? The type of text that we wanted it to generate. So for example, we did something where we had like diagnosis codes and generating doctor's notes based on those codes. And we fine tuned that on actual doctor's notes. But when they become larger, they can do much more, like following instructions. And GPT-3 was the first model that could actually do that. And this is an interesting finding that is called emergent ability. So when the model becomes bigger, it quite suddenly can do much more than it was trained on. And this opened up possibilities with what we call in-context learning. So instructing models to do something instead of fine-tuning them. Right. Is everyone fine so far? Good. So now we've all seen this power of doing prompt engineering, so to provide instructions and maybe add examples. And this is the paradigm shift that I introduced. So before, and now let's raise hands, who of you has ever fine-tuned a BERT model for some task? Yes. Quite some people, right? So this is how we do that, and how we did it, how we still do it since 2018. We take an encoder model or an encoder decoder, and then we have a lot of labeled data. I have typed here much more than 100 examples. So yeah, typically it's a couple of hundreds per category that we need. We only give those examples, so there's no instruction or whatever, and the model is actually being updated. So we fine tune it, and then we have a new model, and we can publish it again on the Hugging Face, and someone else can use it. And this way, people have created models for all kinds of tasks. But now, with in-context learning, we take a decoder-only model, and then a very large one that is so large that it can actually follow instructions when it's fine-tuned to conversations. And then we give it only very few examples. So typically not more than 5, but always fewer than 10. We give it instructions, and the model is not updated, right? So if someone else wants to do the same thing, they have to use the same prompt. You cannot like change the model and then upload it again. Right, so this is the shift that we are seeing here. So let me give an example of a task where this in-context learning is quite powerful and successful, and that task is summarization. So we did this experiment where we compared a 0-shot and 2-shot generative large language model to the regular fine-tuned sequence-to-sequence models for summarization. And the student formulated a prompt to instruct this model. And this was still in the early days. So the student started to do this directly in 2022 in the fall. So he worked with ChatGPT at that point. And later we started working with open source models. But this was still with ChatGPT. And so the model was instructed properly. And then we compared it to these fine-tuned models that were actually trained and fine-tuned on 5,000 training items. So these are those models. So you might recognize some of them. So are there people in the room who work on summarization? Yeah. Okay, not that many. So these two metrics, I'm not going into detail, but it tells us something, and to what extent does the summary look like a human summary, right? So similarity to a human summary. And as you see, all these models are quite close to each other in performance. And what we find is that the LLM, without any examples, so only the instructions, reaches the same level of quality as the fine-tuned models that had 5,000 examples. And if you give it 2 examples, so we call it 2-shot, then it becomes even better on these metrics. So there's also some limitations in evaluation, of course, but this shows that for this task, generative LLMs can be up to the level of fine-tuned models. Right, so this paradigm shift, I introduced it just before by comparing a generative LLM to fine-tuning a BERT model, but even before that, and still we sometimes do that for tasks where simplicity and clarity and transparency is important, is that we train supervised feature-based models from scratch, or sequential models. Not so much anymore, but still, I mean, we do sometimes work with linear SVMs and word-based features to make transparent solutions. So that was the first option that we had. And then since 2018, there became the option of transfer learning, fine-tune a pre-trained BERT model for your task. And then now, since, let's say, 1.5 years, we have the option to do in-context learning. So we instruct a generative LLM. And so for these first 2 options, we needed substantial labeled data. And for in-context learning, we don't. So I did show you that for summarization, in-context learning can be transfer learning. But we don't really know yet how that is the case for classification and extraction tasks. So I know, and I saw also in the program that some people are working on this. And it seems to be, but let's get back to that later in this lecture. Sorry, in this presentation, that it seems to be that for some tasks, for some classification extraction tasks, generative LLMs can be better than supervised learning, but not for all. Right. Is this all clear? Yeah, normally I would say any questions at this point, but let's not do that. That's too complicated. So save them to the end of the lecture. So I would like to go now into this first project, which is about mining experiential knowledge of patients. So this project was executed between 2018 and 2022 by a PhD student in my group. And this was a collaboration also with the academic hospital affiliated to my university. So we had a direct collaboration with medical specialists. And this was a little bit the motivation for this. So we were working with rare cancers, and we were in contact with these patient communities, people who had rare forms of cancer. And these people actually said, well, we as a community, we have so much knowledge about, for example, how to deal with side effects. And we noticed that our doctors, our medical specialists often are not aware of this knowledge. And so this is how this whole project was motivated. So we thought, okay, maybe we can use the information on patient discussion forums as a source to discover side effects that have been underreported, or even the coping strategies for these side effects. And we had a case study here from a patient support group called of the cancer form gastrointestinal stromal tumor, GIST. We had this big data set, and at that point in 2018, we had the first contacts with them, and later we got some more recent data. But at that point, it was still possible to get this data from Facebook. It was donated to us by the patient community. Now we cannot publish any more about this because Facebook data needs more, is more strict to use in research. But at that point, it was possible, and it is very large, 124,000 posts in 14,000 threads. So there's lots of information there. So the question was, can we use this information to monitor side effects for the medications that people use? How can we mine that? So if you want to extract information from text, many of you will probably know, but this is actually a sequence labeling task, because if you want to extract sequences, word sequences from text, the word order matters, first of all, but one entity, one medical, one side effect can span multiple words, and there are multiple ways to refer to the same concept. So what we typically do is we label the text word by word, and we identify where in the text is a medical entity and where is there none. So here's some examples of how people can refer to a headache. I have a throbbing pain in my head is burning. And yeah, all of this has to be linked to the same concept, to the same generic word form, in this case, headache. So yeah, we had some labeled data that we created with help of the community. So what people did, so these are, I would say, experienced experts. So people from the patient community, they labeled data for us. So they said, okay, here in this sentence, I can't fall asleep at all. There is a side effect here that referred to the earlier mention of a medication. And so behind the screens, then this was converted to a sequence labeling data set where it's identified with a B if the word is the beginning of an entity, and an I if a word is inside an entity. And that looks like this. So let me ask again, who of you can raise your hand has worked with this kind of labeling before, this BIO labeling? Okay, quite some people. Yeah, so this is the common way to label data for information extraction, because we want to know where in the text, which words are the entities we're looking for. Here it's important to mention that ADE means adverse drug event, and that is another word for side effect. So how did we go along with this data to actually train models? Well, we had this large data set. We selected a sample, and we kind of pre-selected that to contain personal experiences. We had some automatic classifier for that, but in the end, we had 527 discussion threads manually annotated. And then we used that to train BERT models. So here's again an example. Someone says, since I started on Gleevec, I can't fall asleep at all. So Gleevec here is a medication name, and can't fall asleep is a side effect. For the medication names, that linking is actually not that complicated, because there is like large lists of medication names, dictionary forms. You can do some fuzzy matching for spelling errors. So we did that rule-based, and it had a 93% accuracy. So that was fine. For the linking of the side effects to an ontology, we used SNOMED here, medical ontology. We used a model called BioSyn that we trained on existing data sets. So we didn't have any label data for particularly this data for the entity linking. So we trained it on external data. So here, I can't fall asleep is then linked to insomnia. So how well did it go? First of all, the entity extraction, and we focus here on the side effects. So the medication names, that was fine. That was not challenging. For the side effects, we got this. The recall was 74%, so 74% of all the side effects were extracted. And precision was 70%, so everything that was identified as a side effect was indeed a side effect. The F1 of that is 0.72, and we also looked at 2 human annotators, and they got a pairwise F1 of 0.80. So also 2 humans don't always fully agree on what the entity is, or where exactly does it begin and end. So this is reasonable, but in a pipeline, it also causes error propagation, right? If you then continue next, with this information, there are some errors. The entity linking, if you look at only one identified concept in the ontology, the accuracy was 65%. But I must say, this is on the ground truth annotations. So if you first already lose 26% because your entity extraction is not perfect, you miss even more in the entity linking. If you look at top 5, it's 97%, so that's a bit better. I must say this is an underestimation, because if you look at it manually, there are some cases where the ontology is huge and a bit noisy, and actually the term that was linked by the model is not that bad. But yeah, in general, it's far from perfect. But it doesn't mean it wasn't useful. So the interesting thing is, if you have this large amount of data, you can actually run these models on the whole data set. And then working with the law of large numbers, you extract things that are very common. And this way we identified a large number of side effects. So these are the drugs that we identified. So I had the example of Gleevec, that's actually imatinib, so the most used drug in this forum. So we found these drug names, and each of them associated adverse drug events. And you see, this is a lot of data. And we actually provided this also to medical specialists, and they were happy to see this and to get this information. And interestingly, so that's good about like using these sequence labeling models with embedding, so BERT-based, they can generalize to things that were not in the training data. So we analyzed that 40% of the correctly identified side effects were not in the training data. So it can, based on context, identify that something is a side effect. So one other thing that we did to help the medical community is we compared what we found about side effects also to survey data for this most commonly used drug. And we saw that, so we had to align this manually because it's formulated all differently. But we saw that actually we found some things that were not yet covered in the survey. So this is informative. It can help make better surveys if you provide a better list of possible side effects. Also, the ranking was different, and there were some ideas about that people are not so likely to mention some things in survey if they think they're not relevant, but they do mention them to their peers on the forum. Good. So again, if you have any questions, save them, write them down, and ask them afterwards. And now I go to the next project, which is, I would say, direct follow-up of this previous project. But as I said, we now have to work with different data because we cannot use that Facebook data anymore, which is a pity because it was very rich data. Okay, so I was already saying biomedical entity linking is a challenging task. So I had this 65% accuracy, and it sounds okay-ish, but given the fact that the input is not always perfect, you lose a lot. And yeah, why is it so difficult? So first of all, there are many different ways to refer to the same concept. I had the example of headache or cannot sleep well, but if you look for more like let's say shorter than side effects entity types, things like MI and heart attack are both surface forms of the same concept. But the other way around, you can have words that are very similar in surface form, but actually refer to very different concepts. Here the example of candida and cardia, which are similar to each other in form, but completely different in meaning. Then one aspect is that free text by patients and medical professionals is often noisy. So I know I saw this in the word cloud. Clinical text is one of the most used terms in this conference. So you probably know that if you work with text written by doctors, it's even more noisy than text written by patients because doctors use all these like abbreviations and they make a lot of typos. So yeah, that's challenging. It's noisy. And finally, the number of concepts in the medical domain is huge. So the most used ontology UMLS has more than 3.3 million unique concepts. So you can never make a classification model that has seen all these concepts in training, right? And then it becomes even more challenging if we look at languages other than English. So the UMLS is mostly English. So here is a list of languages included in UMLS. And you see the counts go down very fast. And secondly, large labeled data sets are sparse. And also if you go to Hugging Face, you look at bird models, non-English is way less well covered than English. So in this project, we looked at Dutch. And this is also in the 4D picture project that Paul introduced. We also look at languages other than English, such as Danish and Dutch. So don't worry, I'm not going to give you any Dutch examples. But let me show you. So we were trying to create an entity linking model for Dutch and evaluate it, and we had some challenges. So let me introduce the pipeline here. So luckily there was one bird model for medical Dutch language, which is good. I mean, colleagues already created that, and it's models called medroberta.nl. And that is nice. So there exist fine-tuned versions for entity recognition, for example. So we needed to first announce the UMLS because the Dutch part was very noisy, had a lot of duplicates, redundant information, but also incorrect and noise and irrelevant categories. So that was the first to like improve the UMLS. Then we needed training data for our entity linking. And we didn't do that fully manually, but we created a weekly labeled corpus. I will show you next how. And this is then the full pipeline. So we start with improving the UMLS, then we have this ontology, and we can do a training using this ontology of an alignment model. I will also show you that next. Then with this automatically labeled corpus, we can fine-tune it. We do an evaluation on a manually annotated corpus that already existed. And then we also did a case study on patient support group data in Dutch. So here is a term called SEPBIRD. So who has heard of this, of self-alignment pre-training? Oh, that's good. Actually, some people. So this is a way to pre-train a bird model to do entity linking. And it uses a source like the UMLS, and it's saying, okay, here are two words that are synonyms in the UMLS. And we give them to the model. We say these two words are similar and actually synonym. We want them to be close in the vector space. All right, so this model is trained on knowing which words are the same and which words are not. using something like UMLS. So let me go into this part, creation of the training corpus. So what the student did, which I think was very creative. So he started with this Dutch cleaned ontology, the UMLS. Then he entered a query to Wikidata in Dutch, which of the UMLS terms have an entity in Wikidata, and he found 4,519 entities. Each of these has a Wikipedia page. So now we have 4,519 pages that are about these entities, that are about these UMLS concepts. And then he extracted all the sentences in the Dutch Wikipedia that refer to one of these 4,519 pages. And that gives us a corpus of 51,000 sentences that have these links to these concepts. So all the blue links in these sentences that refer to one of these 4,519 entities are links to the UMLS. Right, so we now have a linked data collection. However, we did some manual evaluation. It was far from perfect. So Wikipedia was much more noisy than we thought, unfortunately. So linking was far from perfect. So we cannot use it as test data. We only use it as training data. So this is done how it works. There is an incoming text. I'm on blood thinners for the last month, but then in Dutch. We need some entity extraction there. And in this case, for evaluating the entity linking, we use the ground truth labeling from Wikipedia itself, or from the test data set. That is given to the model that was trained with the self-alignment, as I just explained, and fine-tuned on our weekly labeled corpus. The output is then an embedding, and we find the most similar embedding of a concept in the UMLS. So this way, we can link blood thinners to anticoagulants. We evaluated that, and so this is throughout all the main categories of UMLS that we included, but let's look at the total here, and we see that compared to the original base model, our model was a 10% point better, so we got a 55% accuracy on that linking. And then if you look at it again, a little bit more lenient, say, okay, we also count correct if the concept that was found was one link away in the UMLS. Then we also counted correct, then we get almost 70%. So that was similar to the results that we got for the English Facebook data, a bit lower. Then we went to the case study. So we got this Dutch patient support forum called kanker.nl, cancer.nl. And it's quite large, 120,000 sentences. And the student actually first ran a Dutch medical NER model and got 368,000 medical named entities from this data. And we then linked that to our cleaned UMLS with our model that we just evaluated to be around 70% correct. And then again, if you look at the large numbers, it gave some sensible results. Like we have like the most common entity is cancer, and it has a correctly linked concept, and so on. So this looks fine, but then we manually evaluated a random sample of 100 mentions, and we saw that it was quite poor. So only 18 are really linked correctly, and in total 38 were linked to either fully correct or related correct. But 20 other were linked to wrong concept, and 42 had an error in the NER. So the first step was the bottleneck here. So this is a challenge. So if you have an NER that is like 58% correct, and you're going to do entity linking on that output, well, there's a problem with error propagation. So to conclude this part about this case study, here's also the code, so you can scan this if you like. I will also share the slides later, and go to the dataset and the models that the student created. So yeah, it was a challenge to do this for Dutch, and named entity recognition can be the bottleneck for entity linking. And an open question is now, maybe for this kind of complex tasks, we can use LLMs with few-shot learning. So that's where the last part of my presentation is about. And I would go into first opportunities and then challenges of LLMs. So we are in my group still working on trying to evaluate generative LLMs, open source LLMs for entity recognition tasks and entity linking tasks. So I don't have my own results here yet. But the first paper that tried to do this in 2023 is called GPT-NER. And so they give instructions to GPT 3.5. I think they also had one open source model. I forgot right now, but they give instructions to the LLM. And they say, okay, I want you to label entities like this. So there's 2 @ and then 2 hash signs around each entity. It gives 3 examples and then an input sentence, and the model labels it. And what they say is there are a few challenges. The first one is it matters a lot what the few-shot examples are. And this is a good point. It's also something that I've experienced with my students, is that if you only give 2 or 3 or 5 examples, it matters what these examples are. So in the paper, they evaluate some ways to select these examples. And the other problem is hallucination. So they found that LLMs are very like over-labeling entities. So they find entities where they are not. And they added some self-verification to that. So they asked the same LLM, are you sure, or can you verify this labeling? And these are the results that they presented. So interestingly, the paper is presented as a very positive result for the use of generative LLMs. So they have a lot of tables in there, but this is the result for the English Onto notes. So that is medical entities. And as you see, it's like the state of the art here. Oh, I'm sorry. The state of the art here, which is a BERT model and actually performs very well here in terms of F1. And then the best setting that they find here for their model with the self-verification, so this is how they selected the examples, got up to 82%, which is a lot lower. But they do conclude, and that aligns with my own preliminary findings, is that when we are looking at settings where the amount of training data is very scarce, then we can beat the supervised model quite significantly with the generative LLM. So this brings me to the idea at this point, and what we are currently investigating is that when we are faced with a task, we're looking at a trade-off between training data and in context learning, where if we have a lot of labeled data, we can still do the supervised fine-tuning of a BERT model, especially when the label set is restricted. So entity recognition, where we have, 6 or 12 different entity types, as opposed to a task where we don't have much labeled data and the label set is completely open or very large. Also, when entities are shorter, fine-tuning probably works better, and when they are common, so they do occur in the training data. But when we are dealing with long-tail entities and they are complex and fuzzily defined, then in context learning might be better. So this is suggested by this GPT-NER paper, and it's popping up more now. But maybe some of you also have some recent experience here. So what I now see, what we're now working on, is maybe we need different resources for different complexity of tasks. So here, since I started on Gleevec, I can't fall asleep at all. It helps to take my meds in small dosages. So in this example, Gleevec, the medication name, well, dictionary matching was already solved basically for this kind of like very clear named entities. So maybe you don't need anything more complex for that. Then they can't fall asleep. I don't know. Would we want to fine-tune a BERT model? Can we still improve the entity linking with contextual models, then link it to SNOMED or UMLS? But these things like the coping strategies, which are very long and vaguely defined and enormously long tail, we might need an LLM to identify them. So this is what we are now working on. So here we see opportunities, but finally, to conclude, some challenges and warnings, and maybe some of them you're already aware of. But as I mentioned, large language models tend to hallucinate because they generate text word by word. It has become a bit better. So I regularly check new versions of ChatGPT to see how poor they are now with hallucination. It was pretty bad in the past, but currently it's better. But they still have problems to deal with questions that have like an error in the statement already. So when did Einstein visit Lancaster? Well, first it starts answering for Lancaster in the US. I said, I mean Lancaster in the UK. And so it answers, but actually Einstein, yeah, I tried to find it, so correct me if I'm wrong. I don't think he ever visited Lancaster. I tried to find it, but it's not nowhere on the web, right? And this occurs more often in low resource topics, and that can be prevented by retrieval augmented generation, right? So this is a big topic now. Let's first get some sources. And actually, ChatGPT now has RAG. So if you ask ChatGPT to write a biography about a non-famous person, it will first get some information. And that is good. But yeah, very often the source is not shown and it's difficult to verify. So there are some statistics here, and yeah, hallucination is still a serious issue also in healthcare. And I think an important thing here is that client satisfaction is not always the best metric for evaluation, right? You can ask people, are you happy with this output? But that doesn't mean it's clinically correct. So yeah, the important thing to keep in mind. Another problem beside hallucination is that there is this bias. So if you ask ChatGPT to write an anecdote about a doctor and a nurse, the doctor is always male, the nurse is always female, and even it's these like terrible writing style. It's not funny. It's not, I don't know. It's very stereotypical. So these human bias, so in text, nurses are probably more often female, but in LLMs, they're always female. So this is a problem if we are using LLMs to provide suggestions to humans. Right, some final things about environmental footprint and also some ethical issues related to how these models were trained. So to conclude, what I think is important in the near future is that we work with open models, with smaller models. We make models for other languages than English. So yeah, Hugging Face is the best place there. I search for medical here. It doesn't cover everything, but you get some. We pay attention to fairness, trustworthiness, and also to the role of the human. So we need to have the human expert in the loop, and I think ideally the human is assisted by AI. So that concludes my talk. If you have any questions, please go ahead. Thank you.
Thanks, Suzan.